for applications. It's still meant to be a general purpose reasoning system. It also uses the non-axiomatic logic, but it makes, as I said, a lot of pragmatic design decisions. And it tries to combine only the stable aspects of the theory and has a strong focus on agency. And also we have chosen C as implementation language. It performs very well in terms of computational resources and speed. Overall, this new system has some desired capabilities, which is, of course, we want to use the non-axiomatic logic because we think it's the right truth calculus and we have achieved a lot with it. Another thing is it should be able to learn from event streams in real time. So you can constantly bombard the system with new information. It should not cause trouble. And when you do this, it should be able to extract sensory motor contingencies. So if you have events from sensors and maybe also events from actuators streaming into the system, it should be able to form relationships like if I see this plus symbol there and I drive towards it, then my battery will get full. For instance, if it sees the loading station and in front of it, it knows, okay, if I turn the actuator or the motor to move forward, then it will reach the loading station and the battery will get full, for instance. Or kind of sensory motor contingencies, it should be able to extract simply from a stream of events. So this is the major paradigm here is event streams. We don't assume a state like in reinforcement learning where we say this is a complete cognitive state and you have to find a mapping from state to behavior. We don't do this. We say we have different events representing different information coming from different sources, from different sensors, from different users. We don't care. So different events coming from different sources. And this streams of events, we want to see certain patterns. And this could be something like something traditionally precondition operation leads to consequence. And it should be very, a major aspect of this new system is to make it really effective in learning those sensory motor contingencies. And it should be able to use them to predict the future and to be able to plan ahead to reach goals. So it's a system which really tries to focus on agency. It doesn't completely focus on the AGI aspect like the Java implementation, because this one is meant to one day hopefully become more human level in terms of what it can reason about and introspection and so on. In this system, there's no introspective reasoning in this new pragmatic design. It's just a simple design which focuses on a system which can learn behaviors and can reach outcomes and plan ahead. And I want this system to become a core for autonomous systems, including robotics. We are currently experimenting with robotics which can learn new behavior on the fly. Unfortunately, our results are still being made. So maybe for the September conference, we will already have some impressive results. But Francesco Lanza will talk more about what we already did in the afternoon. So this new system still follows the foundation of NAS, which is the philosophy that intelligence is the ability for a system to adapt it to its environment while working with insufficient knowledge and resources. This is the idea. If you already know everything, then you can simply compute the solution. If you have a data set which is large enough, sure, you can increase your detection accuracy. There's no magic. If you have the resources and the knowledge, you can do it. We know it. If we have seen it several times, including very impressive machine learning successes, including the AlphaGo system, which is to some degree impressive. But if you really look at what was done, the system already has a perfect simulation available. You can exploit the simulation how long you want. You just throw enough iterations at it, and then you will end up with a system which gets better, hopefully. But we try to focus on something else. We try to make the most out of insufficient knowledge and resources. So if the system does not have the knowledge yet how to achieve a certain outcome, it should be able to gain more information actively, for instance. It should be able to, it should not simply say, I don't have the information, I cannot do it. Or if it doesn't have the resources to compute the optimal solution, it should still be able to suggest a solution. If I look at the Go board, I cannot tell you what is the optimal move. No way for me. My brain cannot do it. But I still can see certain patterns, and I can find some behaviors which I, in my few times I played Go, found to be more useful than others. And so I can try to play Go. And maybe with 10 games, I can already play a bit better than someone who plays it for the first time, maybe. But in any way, we want a system which can deal with the situation where it doesn't have the knowledge to calculate the optimal solution, or it does not have the resources. If you give the system only half of the memory, it should still work. It cannot store as many concepts anymore, only half of the amount. But it should still be able to do something and to find concepts which are useful, and hopefully the most useful concepts still survive, even though it can only keep half as many as before. Also, the system should always work in real time, so you can really bombard it with information. If it works on something, we expect the system to be able to interrupt its task. For instance, we don't want a system which calls a planning algorithm for a certain amount of steps, and then it's not able to react within until it's done or found, or can say it didn't find a solution. Instead, we want a system which can plan ahead one step, and maybe new information comes in at the same time, and it can reprioritize what is currently doing. So if for some reason this new task happens to be judged to be more important, it should be able to interrupt whatever it is doing. So for instance, if there's a dangerous situation, we don't expect it to be stuck in some kind of algorithm or fixed procedure. It should always be able to react and to reprioritize what it is doing, to maybe give up doing what it is doing for something more important. So this is also the key philosophy here, that all system activity is done by atomic inference steps. Sure, atomic inference step cannot be interrupted, but on the other hand, it only takes 1 to 2 milliseconds. This one cannot be interrupted. Okay, but you can interrupt a process which takes multiple inference steps to solve, like seconds or even half a second or 100 milliseconds can already be interrupted. And the good thing here is if you work with atomic inference steps, it means you can have a currency for computation or for computational effort. This is one way of how I look at this. Maybe it's also the reason why Dr. Wang called it budget. The idea is that you can know how much effort certain, or at least you have a measure of effort. So if some algorithm, or if some task demands more inference steps, there's a way to handle this. And yes, that's essentially the idea here. To have some kind of resource currency, so that different computational processes can be compared. So the system works on something more difficult, it can interrupt it at any moment. And why is this important at all? The reason is, and here I really almost missed the point, the most important thing is when you are thinking, the time does not wait for you to finish. The world changes, the circumstances change. So if you think or when the system thinks, the world will already be different. And so it needs to have a way to deal with this. And this is really the heart of this real-time aspect. Another aspect is that new information can always challenge existing beliefs. So there is no hard-coded truth in the system. Whatever information you give it, it can challenge it. It can collect new positive or negative evidence for the statement. So there is no axiom on object level. There is, or beliefs the system have are reversible by new experience. Yes. And also, maybe important is that the different cognitive functions are simply a side effect of the reasoning process. There's atomic inference steps the system takes. Some of them might correspond to planning, sometimes some to some kind of analogy making, or to some compound construction. It really depends on what is inferred. So, but enough philosophy. So another thing is the decision-making paradigm we are following is fundamentally different in some ways to what we see in traditional AI. For instance, this system, OpenNARS for applications, or ONA, solves the temporal credit assignment problem for multiple outcomes. So there is not a single reward signal, and you want to only associate, okay, in this state, if I perform this action, I will get this reward. We are not only doing it for a single reward outcome, but the system, for every event it experiences, it will be able to find ways how to achieve it, for instance. Even when it's currently not a GOR and it just watches the event stream, you want the system to be able to learn, okay, in these circumstances, this event will happen, under those different circumstances, another event. And later, if you then enter a GOR, likely it will already know what to do, for instance, even though it just watched and didn't even receive any rewards so far, or any GOR being fulfilled, because there was no GOR. It was simply watching its event stream, and it was essentially finding certain patterns. Yes, but the point here is also that GORs can change. Even in biological systems, if you look at even simple insects like a bee, they don't learn a single state action mapping. They don't do that. They have different internal drafts. It could be something like bring the powder from the flower. I'm not sure how it's actually called, but there are different, often even different day cycles or certain how to say. So the behavior of the insect depends, for instance, on the time of day, and whether it's currently hunting or not. It depends on some internal GOR. Is it currently hungry? Is it currently thirsty, or something else? So it's not really helpful if you learn a single state action mapping, if what you really want is to have something which behavior depends on the actual internal GORs you have. So if you're hungry, you want to find some food. But if you're not hungry, what's the point? So why use a behavior to retrieving food if you already have enough food, for instance? So you want a system which can handle changing GORs effectively. And you don't want the system to go through training, or even the system learning and relearning its entire Q table just to be able to deal with the situation where the utility function changed. Why did it change? Because the core is different. Because, for instance, in an organism, as I said, you have different drives and different urges which are active at different moments, dependent on their fulfillment. And yes, in this sense, this system is more general than reinforcement learning. We will see it can deal with the situation where you really want to achieve one outcome and one reward, but it can't do it. To find one state action mapping, but it can also do tasks, or it's expected to be able to solve the temporal weighted assignment problem for multiple outcomes. Hence, it should also be able to do it for a single outcome. So it should be able
to. Sometimes your microphone, I think, hits something. Can you check?
Oh, yes. Oh, maybe now it's better. I hope at least.
Yeah, it was good. We just heard it in the last couple of seconds, couple of times hitting something against the microphone. Thank you.
Okay. So but this system still, even though it's not really intended to be a human level AGI, it's a high Gore. Seriously, we don't know how to exactly reach easily. And so this system has a lot of pragmatic decisions, but its decision theory is still fundamentally not reinforcement learning, because we think reinforcement learning cannot even explain the things we see in insects. And this is a big issue to us. So the system can really try to have a more general, a multiple outcome dependent way. So for instance, we want the system to be able to learn from observation and then apply this knowledge it has gained from the observations, even though there was no reward at all involved so far. And this is essentially what we want. We don't think AGI has much to do with reinforcement learning decision paradigm. The next thing, of course, the system should still be able to plan ahead. Or ideally, it should be able to plan ahead. But here, there's no exhaustive search, which, for instance, says we plan ahead for 10 steps to keep in resource bounds and say then if we didn't find a solution, we're screwed. No, it's attention-driven, data-driven selection of course and of events overall. So it has some kind of inference loop similar to what Peter described, and this system a bit simpler. And what it works on, or which course it picks, depends on the priority again. So if it has a higher priority, it will tend to work on it. And so again, the explore and exploit thing is essentially data-driven. It depends on the priority distribution in the data structure. There is no exhaustive search, and this planning process can be interrupted at any time by changing circumstances, by changing course, or anything, or another important task which comes along for some reason. So essentially, it's a bit like a mixture between belief, desire, intention model and reinforcement learning. We have this gap in traditional AI. At one hand, we can learn state action mapping, some reactive behavior. On the other hand, we have this belief, desire, intention model applied in autonomous robotics. They usually don't use reinforcement learning. They use a model which can represent different cores and has a plan library where the agent can select different plans dependent on the circumstances. And that's good. But ideally, we want a system which can do both, right? Which can learn behaviors, but at the same time, plan ahead to reach different outcomes, and a system which does not struggle when outcomes do change. And so essentially what this system is really like, we can do reinforcement learning problems, but it's not restricted to them. It can learn by observations. It can learn how to achieve different outcomes. Or it can learn different or new behavior on the fly, and it can use this behavior to plan ahead multiple steps, as you often want in robotics, because there it's a bit more issue if you run into a war or something, so you want the system to be more sample efficient. And it's good if you can plan ahead and find something which likely will lead to the outcome you want to achieve. So why is it more general than BDI model? The reason is it can learn new procedure knowledge on the fly. Why is it more general than reinforcement learning? Because it can learn to predict multiple outcomes, not just reward. Also, the system can be used for question answering, as we will see. I hope I don't. Oh, okay. So the current state of the system is it can show everything I have talked about. This is not wishful thinking, but it's actually a released version you can try on a variety of tasks already. The special thing here is there's no example-specific hyperparameter tuning between examples. So this is a way to ensure generality. We don't think it's a good idea if you have a model and you do hyperparameter tuning for one task and hyperparameter tuning for the other task. How general is this then really? If you change the hyperparameter, essentially you have something else. You don't have the exactly same thing anymore. In the human brain, you can't just change to some brain surgery for a new task. You have to find a way for the system to be self-organizing in such a way that it can deal with a wide variety of tasks on the fly without any hand-based or human-based hyperparameter tuning. This is one thing. Another thing which you will find unusual here is that you will see this is like a bit like a black box if you use it. We don't call special functions for special tasks. We don't load special modules for different problems. It's really a unified system where we intend not to change parameters across tasks. I think this is really a bit of the heart of general AI. You want it to be general. You want it to not have a human in the back who adjusts parameters or calls different functions for or configures the system in a different way for different tasks to perform. So overall, NAS or any NAS implementation is not a software toolkit where parts are invoked separately, but you will see it's a system where you can interact with NASes. So there's a formal language behind it, yes, but the good thing is it's not domain specific. So unfortunately, so far you only have seen the overall philosophy or the things the system should do. And ideally, I would like to show you now all the internals. But the thing is, on Thursday, I will talk only about the internals of the system. So to use the time effectively, we will now learn how to use the system and what it has to offer. And how it works internally, you will see in my talk on Thursday. That's essentially this. Is because I want to give you a way to use this system. And in previous tutorials, NAS tutorials, we really did not do this, but I think it's a bit of a mistake because you should be able to have a way to use this system. And how it works under the hood, you will see on Thursday. For many examples, it will not even matter because it doesn't work. Or how to say it? It works good enough for most of the examples, so often you can just use it without knowing the internals. But on Thursday, you will know everything about how it's actually done. So for now, we will focus on the usage. So as I said, the system learns by a stream of events. Events can be beliefs, goals, and questions. They just enter the system. How they are produced depends on the application. Could be sensors, could be humans, could be some social network where whenever someone posts something, it will enter as an event. What's the output of the system? Operations and answers. Operations could be something like invoke a motor action, turn an actuator on, or it could also be something like write a message to a user or say a word, something like that. So different operations with which it can interact with its environment. Also, you will see answers because you can also ask the questions about things. It can also answer you in NASs. So this is the overall way how you interact with pretty much any NAS implementation. You don't have any special task-specific plumbing. Instead, you have just events which enter the system, and you will get operations and answers in return. This is ideally how we think an AGI should work. You give it information, it gives you information back. That's how we set up this thing. So what is an event? So event is essentially a NAS term. It could be something like cat is an animal, which is already quite high level. It could also be something low level, like the temperature is low, or temperature is above 10 degrees Celsius. Then there's a truth value attached to this. For sensory events, it will simply encode the quality of the signal. For instance, if you have a sensor which is not very reliable, you define a lower default truth value. But if you have but in most cases, for inputs, it doesn't really matter. You just use some default truth value. That's also fine. But the truth value for derivations will vary dependent on the inferences which are made. But for input, it's most of the times fine if you just use a default truth value. So you don't need to care about this. So you only need to care about what information do you want to encode. Temperature values, or do you want to have some higher level input, like from convolutional neural network, some detection you want to encode as NASs, maybe something like pattern 1 is a cat, and pattern 1 is left to the other detection, which is a fridge, or something like that. You can be very creative in what kind of information you enter into the system. Then the occurrence time, this one is not really set by the user. Whenever you enter an event, the occurrence time will be the current reasonable time, which is an internal clock. And then there's a priority value, which for inputs is also just some default in this system. Then what's an operation? It's simply a function with arguments, which executes, and that's important, in small constant time. So it's not allowed for the system to execute an operation like a planning procedure where it's not clear when it will end. Here, only operations which execute in small constant time are allowed to make sure that the system can keep on reasoning. So like turn your finger or something like that is okay, but a complex invoking another reasoning system, not so. Or some algorithm which you don't know when it will terminate is not okay here. This is also we saw this before. This is not really, what's really different here. What's going on in NAS is an open-ended process. It does not converge to anything. It does not terminate with the answer and then stop. It can work on multiple problems parallel, and it just goes on with its reasoning process. There's no time where you can say no, where the system then stops. It just keeps going. One thing is missing, the answer route. So answer is simply an event which is reported as the best answer to a question event. So is everything. This is the entire IO of NAS. Some information in with some most times default truth value and default priority, and the occurrence time is simply the current time. So you just have to give it some information, and the system can then call certain operations like motor actions. The answers are also simply events given back by the system, which is identified as the best answer to a question of a user. So we will finally get to the hands-on part. As I said, the internals of the system will be explained in detail on Thursday. And so let's go to the hands-on part. So this is a C99 implementation. So you can use any C compiler like GCC, CLang, DCC. Whenever it's C99 compliant, it will run on any POSIX OS, including GNU Linux, Mac OS, Android. It doesn't really have any more dependency. The only dependency is some POSIX API, because we also have a UDP interface for network communication. But other than that, so you can run it pretty much on everything except Windows. But there it's also possible via Cygwin, WSL, some new development where you can run a Linux subsystem on Windows. That's possible, also runs. As a versioning system, you will need Git, or you can unzip it from GitHub, also works. And optional, the test system and other things are programmed in Python. So if you want, for instance, to try the English to Narcisse converter, you will need Python 3 with natural language toolkit. If you just want to run the tests, if you just want to run the system tests, you will not need Python at all. But I will show you part by part. But anyway, what's very important before we dive into this is evaluation measures. We have multiple implementations of this system, and the big question which is always behind our back is, how can we really say one system is better than the other? Ideally, we would compare with other methods for certain problems. Issue is this is highly domain specific. If we compare a general system which can tackle a lot of different kinds of problems and compare it only with a specific, say, algorithm on a specific problem, most times the specific algorithm will be better. But this does not really tell us much, because the system was intended to be a general system which can be applied on a variety of different problems. So we need some kind of way, even if we often cannot compare directly with a domain-specific method, although sometimes it's possible, that's good. But if we cannot do this, we should at least be able to compare our own implementations, right? It would be good. So we thought a lot of evaluation measures, which in this system is taken very serious. For instance, there can be different general purpose measures. Can be something like the answer rate. How many correctly answered questions did the system give in return over the total questions? We can compare this among different implementations. Then we can say, yes, this system gives more correct answers, and so it tends to be better. Or we can look at the average confidence, which gives a measure of the evidence which has been accumulated for the relevant hypothesis. The system which is able to accumulate more relevant evidence is usually better. Not always. You also have to take care here to compare this among a large variety of tasks and not just one particular problem or dataset. That's very the key. If you only compare it for one dataset or one task, you will not get any information about how well the system performs as an AGI system. Next thing, you can do something like average answer time. What is the time demand? How long does it take for the system to give you an answer to certain questions? Or the competence to reach scores over the total scores? Or sometimes you can also use, of course, you can use domain-specific success rates. For instance, for a particular data set, or something like in Pong, you could simply define the hits plus misses, like here. And all those measures matter. And you want to collect those measures over a large variety of tasks. Then you will get some information about. Is one NAS implementation better than the other? And many of those are actually also applicable to other AGI systems. So I hope that in the future they will also give us a way to compare also different systems. But often, if you compare it just for one specific data set or problem, it doesn't really give you much information if the system you compare with can only solve this particular problem. However, there's the issue if you have a lot of metrics. There's the issue how to keep track of it. You make a change. Some metrics will get better, some will get worse. It's a problem. But you can at least do, it's not a complete solution, but you can combine certain general purpose measures. So we have, for instance, the success rate. So we combine the answer rate, the average answer confidence, how much evidence was collected, and the competence in terms of score fulfillment. And so when it answers more questions, it's better. If it fulfills more scores, it's better. But of course, this is also sometimes problematic because maybe this new system is just only better in question answering, but is not really good in decision making. But this is at least one way you can combine those different aspects in terms of question answering and decision making into one value. And yes, and then you can create a combined loss values. And here the restriction is you want the hyperparameters not to change between tasks. This is really important. If you want an AGI, don't touch the hyperparameters. Find values which work for a large variety of tasks. Maybe fundamentally, mathematically, maybe there will always be environments it cannot handle. Maybe it is that way. But it's sufficient maybe if it can deal with the environments we humans are used to. Maybe that's enough. So this is not really touching on the theoretical issue if there is even a general AGI which works for all environments. I mean, there are theoretical models like AGI, but this one is not computable. So if you make it computable, you have to make certain compromises, and that's a difficult issue, how to avoid biases. I would say that it doesn't really matter. The biases are not that important. You need biases. As a human being, you have inherited a large bunch of biases over thousands, millions years of evolutions. You have inherited those biases. Those biases are not the core of your general intelligence, but they at least let you distinguish your brother from your father. And so we are not really against biases. As long as they are not task specific, as long as they work in a quite general way in the environments humans are exposed to, it's not too bad. So we don't depend on some theoretical fact that would be that AGI has to work in any environment. We don't claim that. And I think it's a distraction of what we really want to do, to have a system which enhances autonomous systems overall, systems which can learn by their own experience in environments similar to the one we live in. So this result section, actually, we will not capture now because it's also part of the talk on Thursday. There are different examples we have used the system with. Maybe I will touch one just to illustrate how we use metrics. For instance, because metrics really matter. And for instance, we did one project with Cisco, and here we will just, for instance, look at the prediction. In this scenario, the system watches a live stream of cars or traffic. So, and it has a convolution, or it has a sophisticated tracker as a tool. which gives it the information about what is a car. Whenever it detects a car, it will know, okay, this car 67 in this case is at this location, and it receives this information as input events. And after some time, you will see the system derives expectations of where the object will be in the future, which you see here with the pink arrows. And here it's already important to have metrics. You want to be able to measure how well the system predicts, right? How can you do that? One way is to compare with ground truth. Does the car really reach the predicted location in the predicted time, or does it not? So you have a measure which simply tries to see if the object really reaches the predicted location at the predicted time. And you can do that. And then you can capture metrics of how well the system predicts over time. What we found here is with this combination of this tracker, which uses ConfNets under the hood, we combine it with reasoning, so we don't have to train the entire neural network to predict. It simply has to give us the detections and the locations, and then the system can learn very data efficiently in a matter of seconds. It can learn, for instance, the movement of cars. And I think that's impressive, and I think that's important for AGI. It's not really that important if you can increase your accuracy over many years of training them. It's important if the system can work under insufficient knowledge and resource, if it can make the most of the limited smart data it has available. And this is what we focused on so far. Yes, and so metrics are important because else you cannot measure progress. And so we want to be able to compare different implementations, and we also want to be able to compare if we make a change, is it then how does it make the system better or worse? The more information we have here, the better. Yes, but now let's jump to the hands-on part. So you will need those things, so you can most likely on Windows it's a bit more difficult. Sorry, you could use your phone if you want. There's an app called Demox. It has a terminal inside. This is one way you could also run the system on your phone. But other than that, if you already have a Linux or a Mac available, this would be best to use this one here. Sorry if I use some Windows users here. Yes, and any compiler will do. So let's just do this. So I'm just now let's open a new terminal. So we make a new directory called workshop 2020. We go into the directory, and now we clone the system. I hope you can see it because the text is a bit small. So the system is now cloned. So we see a folder where we go into. I will give you some time to replicate this, and then you need to execute build.sh, then it will build the system. I would say in the meanwhile we can do some question answering in case that the question popped up, because I want to give people some time to. Some people might want to follow this, so they have the time. So if there are any questions in the meanwhile, you are open to ask.
I'm very interested in this mechanism that does the interruption of a task. So while it's not, I mean, I could bring specific questions such as, well, how do you guarantee that this mechanism is still reactive over time? I mean, that it doesn't basically take longer and longer over time. I mean, overall, I'm just curious about this whole mechanism. If the tutorial touches upon it a little bit, that would be great.
So you want on Thursday there will be a very detailed presentation about this. So now I can only give you a very short illustration. CMD plus, that's a good idea. Whoops. CMD plus, maybe I'm on the wrong. Let's try here. CMD plus, thank you. That's better. Now the screen is larger. In case you want to make a screenshot now, make it, because I will answer the question now. So git clone, then it was go to the directory, and then it was build sh. Okay, sorry for the waiting of answering of a question. So the idea here is that there is no explicit algorithm. So we really want the system to operate in a very data-driven way. So events come from sensory channels, then they can be combined from multiple modalities. And what's important here is this thing in the middle. This thing in the middle is pretty much like the bag Peter described. So events are ranked according to the priority value, and the high priority events are selected for inference. So they will be selected to form concepts and to select beliefs from the memory structure. So for now, the details are not that important. Really important is we select the first premise here from the attention buffer, or cycling events queue as occurred. So we have the first premise. Then we somehow sample the second premise from the memory. This one you will hear on Thursday. So now we have two premises, which we can do two kinds of inferences. We can do syllogistic inference, for instance, based on a common subterm, which I called here semantic inference, or it can be something which uses implications. Then here I use sensory motor inference here in the system, and it's related to a temporal. If you want the system to predict an outcome, it uses some implication of the memory. So the implication is the second premise, and then it goes here. But in any case, it's always this loop. To select the first premise, to select the second premise, to do inference, to give the result back to memory. To select first premise, to select the second premise, to do inference, and to get the results back into the attention buffer. So it's always this loop. In this new system, it's actually two loops because I separated the concern of dealing with implication and with inheritance. I think it's the best way to look at this way. So this is mostly inheritance related reasoning, and this is mostly implication related. But in any way, it's just a reasoning loop. It's just selecting based on the priority value, deriving tasks. If the derivation has deriving event, I mean, if the event has a higher truth value, it will tend to have a higher priority. If it's, but it cannot exceed in this system, the child task priority cannot exceed the parent tasks. So here is a very simple budget system, much simpler than in the Java version. It simply multiplies the truth expectation of the result with the parent task priority. That's the new priority to go here. At the same time, the the selected event will also go back to the attention buffer, but with a, like in Java, reduced priority. So whenever we use an event, we reduce the priority when it goes in a loop. And whenever we derive an event, when a derived event enters here, its priority is simply the truth expectation times the parent priority. So it's a very simple budgeting. So the priority of this child is lower than the priority of the parent here. And the priority of the items decays over them. That's all it does. And which kinds of inferences it does, maybe I have something here. Can give you, so for instance, semantic inference would be if S is a M and M is a B, then S is a B. So if Garfield is a cat and a cat is an animal, Garfield is an animal, for instance. It also has abductive and inductive ones here, but then it also has this sensory motor inference, which deal with implications, like if it has the first event is a and the second belief sampled is a B, then we can, if this one happened before B, if B happened after A, I mean, it can derive, say, an implication. And it can use this implication then in the next inference step if it selects A, and if it selects this implication, a second belief, it can predict B, for instance. Similar thing, it can do subcoding if it has a G and it has an implication link between concepts. So if it G enters, so if it uses this as a second premise, it can derive A. And here, what's relevant, when there are competing alternatives, it always selects the one which has its precondition already fulfilled the most and which is also the strongest link. So it tries to use the truth expectation to select the candidate which precondition is most fulfilled and the link is most strong. And this operation it will then choose to execute. But this will be explained better on Thursday. This is just very quick way. So it can derive belief events to predict the future, and it can also predict. It can also generate subcores to go back into this queue. So instead of an algorithm which plans ahead or something, we only have this attention buffer. We select first premise from here, then a related one from memory, and the result go back into the attention buffer. It's only this attention loop. And all the examples we have only use this picture. There's nothing else.
So it's not exactly that there is an interruption mechanism. It's more like something that is not interrupted. It's just the continuation is selected over and over, right?
Exactly. Mm-hmm.
Right.
So the interruption is reached by not having things to interrupt in the first place, essentially, because each inference step is just an atomic thing taking a very small amount of time. You don't have the issue to have something you need to interrupt. That's the idea here. So it goes step by step, always selecting what's currently contextually relevant to do some inference. And so if it plans ahead, it's usually, it can be many inference steps which are necessary to find the solution to record or to plan ahead for a certain outcome. So the entire process of planning ahead is reduced to inference steps which are realized with this always select the most relevant thing. Things to select a belief, infer some other events or subcores you can work on. And this repeats and repeats and repeats, and or the prediction behavior you get and subcoring behavior is just a result of this picture. So I guess at this stage you have followed. Maybe I should look into the chat if I did not miss something relevant. Okay. So we cloned the repository. We changed into default of the repository, and now we build it. Just build sh. Now it will compile and write some warnings that it not yet eliminate. So now we have the system. And now we can see if it works by simply executing the nar. So simply type ./nar and then press enter. It will run dozens of test cases. And if successful, it will say all tests run successfully. If you wish to run examples now, just pass the corresponding parameter. So so far, I did not really want to bother with any graphical libraries and stuff. So all those examples run in the terminal. So let's just pick an example. So for instance, we have bong here, so we can simply pass bong. Some of them don't have a visualization yet, but bong has a ASCII visualization. I hope it does not flicker too much over the zoom, but let's see. So it does not know how to play it. It just observes some stuff. It sees the ball is on the right. It notices when it executes an operation. Now it sees the ball is on the left, maybe. So it's just different things happening, streaming in as events. But it has the goal to hit the ball. It does not yet know what the score means or how to achieve it. But sometimes it hits it. And it sees maybe, hopefully, some temporal relationships to the state of hitting, to hit the ball. And so it learns, okay, when the ball is on the right side, maybe I need to invoke right. If it's on the left side, maybe I need to invoke left. And if it already got it, it looks that way. You will see the hits and misses ratio to increase. So the ratio is actually hits divided by hits plus misses. So you will now see this ratio getting closer to 1 if you let it run longer. So it really understood how to reach, how to get the ball to the bat in different circumstances by invoking left and right operations. Of course, we have to make sure this does not only work here, but also in other. We also have a slightly more complex version of bong, also with slightly different sizes of the bat, just to make sure it's not just luck. Of course, we have also a way to randomize the initial. How can I make it smaller? In this case, I need to make it smaller. So, and here, this is a slightly more complex one because here it needs to invoke a stop operation, because else it will just keep going. If it executes right, it will just keep going. If it executes left, it will just keep going. But there's a stop operator it can use. And as you see, also has learned it very quickly how to do this. This is just one thing, but bong is for many not too impressive. So maybe we can show something else, something like test chamber. Now test chamber. What you see here is a ASCII visualization of a room, and the room has a door, and the door. So there's a room. The room has a light in it, L0. This one has currently state 0, meaning it's off. Then there is a switch, S2, which, as you can see, is supposed to turn on the light. Then there is a door in the room, it's S1, and this one has a switch to open the door. Currently, the agent is this one, this arrow. It's at position S0. And now I can tell the agent, for instance, I want to show learning by observation. So I will control this thing by myself now. I will say, why is it not showing? Go to S1 is B, go to S0 is 1, so I can press A, B, enter, A, B, enter. And so I just let it walk between S0 and S1. And I could now ask, I could give it the goal that it should be at S1, which is B in this case. And you see it walked there based on what it has seen before. A similar thing I can do with the door now. I can activate and deactivate this G and H. So I can open and deactivate the switch to open and close the door multiple times. Then I can manually walk back to S0. If I now say the door should be open, it's already a multi-step decision-making experiment, because it has to realize, okay, it's currently at this location. It needs to reach this switch 1 first, and then it has to invoke the activate operation. So if I say door should be open, so it needed 2 inference steps, but it went there and activated the switch 1. So it has already learned how to get to the position of the switch for the door, and it has already learned that the switch to the door opens it. So you can try simple experiments here in this domain. If you spend more time, you can also teach it how to get from here, to open it, to go to switch 2, and to turn on the light. So it will also be able to learn more complex behavior, like go into a room and activate the light in there. This is one example, very basic example. What else can I show? Another example, which is maybe a bit more interesting to some, is a simple robot simulation. The idea here is simply to collect food. There are also wars in the environment, which, of course, if you're stuck, the system needs to turn, and also it needs to learn how to collect food. And here, the vision of the system, it's in bird view essentially, but the system sees the world from a robot perspective. I will show you here. So it sees the arrow indicates the direction it's looking. It's the red thing here. And now it's looking to the right. Now it's looking into the war. At first, it just invokes motor babbling, trying random operations. Here it sees there's a green object in front of it, another green object left to it. And it doesn't take long for the system to figure out how to collect those green things. And also, you will see it avoiding wars often. So it also just sees what's in front of it. And so it's a one-dimensional retina, one could say. And it has to learn what operation to invoke in what situation. If it sees the green thing on the left side, maybe it should invoke the left operator to make it appear in the middle. And then maybe try the forward operation to drive towards it. And you see it often takes a bit of time, but there were already a few examples where it seems that it got what it should do. Usually it just takes a minute or two. But the idea here is the same, it just receives events those events give it information about what it sees. And if there's a bar in front of it, or a green object in front, or what's on the left side, what's on the right side. And I think now it got it. So as you see, it collects stuff it sees, and tries to avoid the obstacles in the way. But it's of course, if this is all you want to do, a reinforcement learner is maybe more effective. But point is, it can also do it. So you don't need to go back to reinforcement learning. And what I want to do with this environment is to make it more complex, to add, like in the previous example, to add a door here, or maybe a switch at another place. So it has to learn to use the switch in order to get to the other room, and so on. This will be the next steps to make the environment a bit more interesting. So yes, but it seems to get it. Sometimes it takes a few inference steps where it does nothing. This is just a natural thing which happens with this inference loop. Sometimes it selects items which might not be too relevant. So, and valid reasons, time is already going. So whenever it waits, it's essentially thinking about what to do next, essentially. So it's not like in a reinforcement learning environment where the agent is expected to output an action in every frame. That's not the case here. And also sit back and reason, and when it's ready, it will invoke the next step. That's the idea here.
If you set the default confidence to 1 instead of .9, is that going to make any difference, or?
1 would not work, because confidence essentially is the total evidence divided by total evidence plus 1. So it essentially, confidence 1 would mean it would have infinite amount of evidence for the truth of that statement. So this is a case. So default confidence does not really matter much. It could be 0.9, it could be 0.5. As long as it stays the same over its lifetime, it will work. But it cannot be 1. It just has to be some unit of evidence. So we wanted to add the same evidence for the same observation. And
is that going to make, I mean, is the default confidence is going to make a difference in the truth value of the internal relationships that are being built, relating the inputs and the goal, or?
It's a bit like, mostly it's like currency. For instance, I could scale up all the prices and for all different things by a factor of 10. It would not change the money flow, essentially. It's as long as the relationship between the things, like a car should still be, say, 10 times as expensive as a computer on average. As long as the relative measures don't change, I could add a scaling factor to the currency and it would still work if it's happening on a global scale. And here with confidence, it's a bit similar. What really matters is to give it a certain amount of positive evidence for a certain input. And so I just give it a certain amount of positive evidence. And this amount of evidence I give it, I just give it some fixed value, which does not need to change over its lifetime. So each sensory value has a certain amount of evidence when it reports the value. as long as the relative, so important are the relative numbers. Those are really what matters. So if I set a different default truth value while the system is running, if I change it, this can cause issues, of course. But most times, if you just set a certain default confidence at the beginning, this will, and you don't change it, then you're good. It doesn't really depend on any particular default value, as long as it's larger than 0, meaning there's some evidence, and larger than 1, meaning it's less than infinite evidence.
And if, for instance, one of the input, for instance, Ethan is actually provided with some noise, would you benefit by lowering the confidence of that input?
That's a good question. It's one way. For instance, if you have an unreliable sensor, you could make the reliability, use the reliability of the sensor as the confidence. That's good. It will improve it, but only if you can really be sure that this value you use is really reflecting the certain,
right.
How well the sensor performs. Else it's better to just use a default. But if the sensor doesn't always report the right value, the system will learn that the hypothesis it builds based on this sensor pattern will not be reliable either. So it will automatically, if the sensor is not reliable, the hypothesis on top of it will also not be very reliable. So you get it for free to some degree. So it does not need to be
right.
input.
Yeah. I mean, you can view a sensor as never being faulty, basically, because what's faulty is your abstraction of the sensor, what you, right. Okay.
Exactly.
Interesting.
Maybe one more thing I can show is there's also a way to interact with the system directly. There's a shell. With the shell, you can directly use NASIs for communication. So you can even introduce higher level terms like Garfield, like the example I mentioned before. Garfield is a cat, and cat is an animal. You will see derivations like Garfield is an animal. If Garfield is a cat and cat is an animal, hence by deduction, Garfield is an animal. And with a lower confidence, you will also get conclusions which are not intuitively read, but this is reflected in the low confidence value. Also, you can simply enter events like A, B. Let's open a new one, else we have intermediate derivations and it's different to interpret the output. Let's say we have A, and we have some steps later, we have B, and we have C. And you see, it derives certain hypotheses like A leads to B. This is not something the user has started, but the system has simply seen by the events it has experienced. And more interesting, like a sequence belief that A and B together leads to C. And so it forms all those competing hypotheses. So if, for instance, it has A, B, C, A, B, C, A, B, C, then it has an A, but there will be no C, or it has a B alone and there will be no C, then it will get negative evidence for B gets C, and it will get negative evidence for A gets you C. And on the other hand, this pattern will then prevail, because if it happens to be that way, that always C happens after A and B, then it will be this hypothesis, which even though it will not be the hypothesis of the highest confidence, it will be the hypothesis of the highest truth expectation, because the other hypotheses have negative evidence then. So you can play with different input sequences and see what the system will predict. So for instance, if we enter now A, I would want the system to predict B, right? For instance. You see, this means event. Maybe this one I should have explained earlier. This is simply a meaning event where you also see the occurrence time when it predicts it. So when now I entered the A here. I entered this A after I have shown it ABC a single time. It predicts B with our occurrence time of 10 and a C with our occurrence time of 12. So it has from this B has predicted B and C with C happening after B, which is red. So you can use it for sequence predictions. But to show you a more interesting example, I will show you an example of the old version so far, because I'm running out of time. Is there any question here?
Yeah, so it's able to predict the occurrence time, but wouldn't there be some kind of like different possible times? I mean, I didn't have time to like follow everything, but in general, right, you could have C that could occur at time 12, but maybe also at time 11 and at time 13 with different frequencies and confidence, right?
Mm-hmm. That's true.
And so it is going to derive all the possibilities, well, given that the loop of selecting the next inference can go that far, but right.
Mm-hmm. So the key here is for the system to learn the timing between the events. So what's not visualized here, in every implication, there's also implicit timing information. So for instance, we entered this A at occurrence time 1. Then we entered a B at occurrence time 3. And so in this implication, there's some metadata, which is not shown here, which is +2 steps. A leads to B in 2 steps. And so if I now enter A here, which was 8, occurrence time 8, because reasoning system has already done some inference steps, the internal clock has progressed to 8. So now it needs to take into account that there is a difference of 2 here between, oops, what did I press? Okay, we see it here. So A we entered at 8, and B then occurrence time 10. So it took into account the experience timing between the events. So that's also relevant. So for implications, it also learns the expected timing. So for instance, it learns that if you have an energy saving lamp, it will take longer for the outcome to be achieved, for the light to go on, than maybe for LED light. So it can learn those kinds of relationships.
And so you say that the timing inside the predictive implication is hidden, it's not represented. How is it represented internally, and how do you deal with having different implications with different timings? I mean, the same implication with different internal timings.
Mm-hmm. That's a good question. The idea here is to use what we call temporal projection. So there's a similar issue if you have, for instance, event A, so say a sensory reading of temperature 40, then 10 milliseconds later you get another 40, then another 40, another 40, then you get suddenly a 0, then a 40 again. What you want is the system to be able to revise events as well, right? So that it can, for instance, so that it can combine the evidence. But the thing is, the occurrence times are different. So how to do this? Similar with implication, you have A implies B with a time difference of say 1 second, and then you have an energy saving lamp, and it takes say 5 seconds between pressing the switch and the light going on. So how do you combine those hypotheses? And the idea here is very simple. We just penalize the confidence based on temporal distance. So if the closer two events are to each other, the more can those evidences to be taken to happen at the same time. While if one happens far apart, then if I penalize the confidence of one based on the distance, it cannot affect the other much anymore because it will already be low. So it's a very simple idea to penalize the confidence based on the temporal distance before revision. That's the idea here. So the higher the temporal distance, the less can the evidence be taken for the other event to be accumulated.
It makes sense, I mean, it certainly intuitively makes sense. I'm wondering, because it is based on some assumptions that seems to be a little bit hidden, I mean, implicit. Do you have like a more explicit, I don't know, mathematical justification for the way the scale, well, the scale, rather the distance, not the scale, affect the confidence? Or is it more like, well, you've tuned something and that seems to work, so it's good enough?
That's a good question. It's more intuitive, I would say. It's essentially, I mean, the entire non-axiomatic logic is to some degree based on the intuitive idea that the hypothesis can have positive and negative evidence. And of course, then you can define a ratio like the positive evidence divided by the total, and you get the frequency value, or you can say to map the total evidence to a value between 0 and 1, and you get the confidence value. So it's, I would say, even though there's a formalization, the idea behind the formalization is actually intuitive, and I think that's the right approach. It's questionable. I don't think we can prove. We can say this proof calculus is the only valid proof calculus to deal with uncertainty. I don't think there will ever be such a thing, but we can create some formalization, and which, for instance, makes sense according to some interpretation, like in probability theory, based on probability spaces, and we can formalize our ideas, and we can see how they work for different circumstances. And non-axiomatic logic is designed for the case, for instance, where we don't know the exact form of the probability spaces. So what can we then rely on if we don't have information about the probability spaces? Multiple approaches. We can use statistical estimation techniques to somehow find ways to infer somehow the shape of probability distribution from our data, or we can find another way which doesn't have a direct or intuitive mapping to probability at all. For instance, in probability, I guess there's a similar issue in the OpenCog system. You cannot have a global probability distribution because it's computationally expensive to update it, even though it's possible. But you can do something else. You can allow for local probability spaces. But when you do this, how do you decide? How do you take the confidence? In our case, the confidence, I'm not sure if it's also called like this there. It might be called strength or something. But how do you take this measure, this additional measure into account? For instance, let's go to a very simple example. You have a coin, and you flip it, and you have 2 times head and 2 times tail. Somehow you don't want this to be the theory that you get head and tail 50%. You don't want this theory to be as strong as, say, when you tried it 400 times instead of 4 times. You want somehow to have the total. You somehow want to take the size of the sample space into account. How many samples did you already take? And this idea is outside of probability. This cannot be, is outside of the axioms of probability theory when you want to take the size of the sample space into account.
Well, yeah. I mean, in OpenCog, it's not exactly outside, but we have a second order probability. So well, it is outside in the sense that it's a meta distribution, but it remains within the theory of probability.
I'm not sure if remains inside is the right wording, because in the moment where you add additional axioms, you're extending the structure, right? You're not, the truth, the statements you derive, they are not justified only based on probability axioms.
Well, I mean,
there are additional theories you can put on top, like second order probability and something like Dempster-Shafer theory, but they are not, how to say, you cannot prove they are right. You can put some axioms together where you think it makes ultimately intuitive sense. You cannot prove the axioms are right.
Well, yeah, sure. I mean, yes. I mean, yeah. I agree.
And it's a bit counterintuitive that null does not at least try to extend the axioms of probability theory, which is, I agree, this is also difficult. Why don't we also use it? And the thing is, let's say, actually, for instance, if the confidence values are very high, ideally we would want it to use probability theory. Because if you look at the formalization of probability theory, you have the limit case. For instance, if you want to work with empirical evidence, you could say amount of heads for the coin case among the total times you throw it. But if you want to say this value is a probability, you actually mean you have tried infinite amount of times, because the ratio is defined as a limit. And so in NAS we don't have it, and I don't think we can justify it. We cannot just treat it as a probability value, because we cannot throw the coin infinite amount of times. So what can we do? And that's a good question. And I'm not saying that the thing null does is the only right one, but I guess there is not much more left than say, let's find some things which make intuitive sense and let's try to formalize them and see what we can make with it. It's difficult.
Right. Yeah, I see the rationale.
How much time do we have left?
15 minutes.
Okay.
Yes,
But
we're allowed to go over a little bit into the break if it's needed. So.
Okay. The difficult thing is really how to deal with uncertainty. This is really a key issue, and because if you cannot prove that the axioms are right, what can you do? And but at least you can define some proof calculus which can work under uncertainty, under certain conditions.
Yeah, I mean, it seems like, well, from some even preliminary experiments with PLN that actually you probably need not just a second order distribution, for instance, but you would need an arbitrary order distribution. I mean, if you really want to be accurate. But
and are you currently using second order?
Yeah.
Oh?
Yeah. So that's how confidence is mapped into how the second order distribution is going to look like. So if the confidence is 0, then it depends on the prior. But if you have a Bayesian prior, it means that each probability of the event are going to be equally distributed. It's going to be a uniform distribution. And so if you take, for instance, a coin, if you have no knowledge about this coin, the probability of getting head would be anything between 1 and 0. And as measured as you're going to throw the coin, you're just going to narrow the second order distribution to an actual probability. But of course, as you said, in order to have an actual probability, you need to throw an infinity, of the coin, an infinite amount of times. When you have something which is just a binary, something that has a binary state, and all you have is direct evidence, it works pretty well. But as soon as you start to reason, then first the distribution that we use, which is a beta distribution, which is perfect for a binary event with direct observations. Then when you start to combine reasoning, then the beta distribution is no longer so good. And the more you reason, the less the beta distribution is going to approximate the actual second order distribution. And the thing is, I'm not sure yet, but maybe it's just a lack of resource, but it feels that, at some point you're going to have to approximate the confidence itself. And then, well, if it's an approximation, well, then you have a certain, you need to have a confidence over the confidence. And so then you need a third order and so on. So these are tricky questions. Yeah. Yeah.
Agree. Very, very difficult
Yeah.
to handle uncertainty properly. And I'm also not sure if it's the final story what we use here, but it's just at least a formalization where we can at least make sure that we don't violate at least the null axioms, so to speak, because the way truth value is defined in NAS, we do not need to assume that we took an infinite amount of samples. So we don't have an assumption we possibly break. So we stay mathematically valid, so to speak, to our axioms to some degree. So to the formalization of the non-axiomatic logic. Which does not imply that it's also the perfect truth calculus overall to deal with uncertainty. Yes, so it's really justified according to this intuitive thing that hypothesis can have evidence which votes for it and evidence which votes against it. And this is really what the system tries to utilize when it makes its decision. It tries to, its decisions, it tries to, for instance, it tries to rely on the most, on the most truthful hypothesis, because often the system might not even know a good solution, but the worst, the best solution is still better than none. So even though it might only have a clue with a low confidence, it might still be better than nothing. And this is, so it can happen like in the beginning of our procedural learning examples. The system only has a very, very low confidence for the hypothesis, and it will simply, in this implementation, it will simply tend to pick the best, or the hypothesis which has the precondition most fulfilled and which has the strongest implication in terms of truth expectation. So actually, it's a form of deduction, but how this works exactly can be read in the non-axiomatic logic book. So it essentially it wants to always use the hypothesis which, to its own knowledge, is the best one currently available, even though it might be a crappy hypothesis. But how can the system know? Another thing I want to show you, as we have some minutes left, some simple English example. So we have the script called English to Narcisse. It makes it easier for people to interact with the system because it can pass simple sentences to Narcisse essentially. If we call it like this, it will only do the Narcisse translation. The translation. For instance, if I say then it will generate this Narcisse. But in this case, it only acts as the translator. But we can invoke it a bit differently. We can use a Unix pip to say I want to pip this output into the NAS shell, which you can do like this. So you launch the English to Narcisse translator and you pip the output to the shell of NAS. This you can do. So I think it's already ready. So what did I write? A cat is an animal, I think I wrote. And if I say something like Garfield is an animal, they could then ask another thing. If you don't want to see the derivations, you can simply put star volume is 0. Then you will not get distracted with derivations. And I could ask the system, is Garfield is an animal, for instance. And it gives this answer. It again translates the question into Narcisse, and it answers in Narcisse. But at least it lets you interact with the system more easily because you can simply write a simple sentence and it will map it to a Narcisse statement. Doesn't make much sense. The dog likes hot potato, but it directly maps it into the corresponding Narcisse statement. I could ask who likes hot potato. And it says, for instance, I can ask who likes hot potato, and it says, the dog likes hot potato. At the beginning, the Narcisse is a bit hard to read, but the language interface is also a way to make it easier to learn to use the system because you can type something in, and then you can see how it would be represented in Narcisse. So then you can also have understanding of how you could encode something similar yourself. Like in this case, in this case, we have an inheritance statement. So the dog is something, this inheritance. The dog is a special case of something which likes a hot potato, essentially. This parenthesis indicates a property which it extracted from the adjective in front of the noun. So what this does is very shallow semantic parsing. It does not really try to find a meaning for the terms or for the words in terms of meaning or grounding in terms of meaning. It does only translate it, and the system has to relate it to the other events, and this is what gives those terms actual meaning. So we do not try to have a deep semantic labeler, which something like a semantic raw labeler. We don't do this. We simply translate it into terms, and the meaning of the terms has to be learned by the system itself, based on the context, based on the other events which are happening. And we have, for instance, some story understanding examples.
I'm sorry. What difference is that going to make to the inference system that hot is an adjective that it's between brackets as opposed to say potato? Because both are concepts. I mean, I guess that. I mean, they have a conjunction, but why? Like, yeah.
That's a good question. This is like a set. So I could also have multiple properties, like dog likes hot, yummy potato, something like that. So for instance, as an example, I could also say a cat. It doesn't have a meaning for a cat. What is a cat even? Let's use dog, because we use dog here. I could say dog is meowing, barking, barking, annoying, for instance. So you can have multiple elements in this bracket. So it's like a.
It's like a conjunction.
Oh yes, exactly.
Right.
Intentional intersection, or actually intentional set.
Oh.
Exactly. So you can have something like a dog is barking and annoying.
It has to do with intentional knowledge.
Exactly. So those are properties essentially, barking and annoying. So I could ask, yes.
But I mean, why is that different? Why is that different from potato? Because I mean, potato is also a concept. Can be as abstract as hot, depending on the environment, right? Well, I mean.
I see what you mean. The difference is also to distinguish the thing from the thing having the property. Like you can think of color as a concept. For instance, you can say red is a color, red, for instance. But at the same time, you can also express that something has a color, like dim. Let's just call it colored. Sorry, let's just use the intentional set. So I could say red is a color, but at the same time I can say dim has the property to be red. The difference is, imagine if this one would be missing. It could infer that dim is a color, but that's not the case. You want to distinguish the concept of the color red from something having the property of this, the property this concept represents. This is the basic idea.
Okay, that sounds very interesting. Okay.
And this is also interesting from a natural language perspective. Actually, what I found is that many, at least simpler natural language often maps in very natural Narcisse statements, like here, dog likes hot potato. You could almost read it from left to right. It has a very natural representation. And so we hope that we can soon do more on natural language. So far, it was not our main priority, because at least for me, always sensory motor contingencies were the main thing. how to learn from event streams, how to learn to reach certain outcomes you want to achieve, how to plan ahead multiple steps, even though you don't use an explicit algorithm, and so on. But here, the language domain also, I think there are a lot of low-hanging fruits which we should explore, because to some degree, at least English, I'm not sure if it works for every language that well, but most English has a quite natural encoding in NARSIS, which is something to explore further, I guess.
Patrick, I have a question, if I may.
Oh, yes, sure.
I understand that this is quite experimental and not really a product yet. This natural language thing, but I'm intrigued by it because you're approaching it from a very I think practical and interesting perspective. The way I like to think of it, and correct me if you disagree, but it's kind of like saying, okay, we're going to give NARS caveman language properties. You can grunt and you can point, and you can talk about things here and now, sort of, but maybe not really complex things. Now, the reason that cavemen talk, or if you're in a foreign country and you try to ask questions where you're not very familiar with the language, is sort of a comparable thing. The reason that it works is that a lot of knowledge is shared with respect to the context. So there's some reasoning that happens. They couldn't be asking about some ancient philosopher, because they're standing here and they're talking to me and they seem to be going somewhere, kind of, if you're asking for directions. And so my question, if I can get to it, is sort of about, have you thought about how NARS might be able to do that? I started to, just to explain, I started to think about like, wondering whether this natural language interface, if it's so simple, if it's really brittle, because then it's not really that useful actually even for a newcomer, because then subtleties in how you phrase things, even if it's valid natural language, might not work for NARS. But if NARS had this sort of caveman ability to think, okay, here's the context, and so let me use reasoning to figure out like what is the most likely thing that this could be about, etc., then that would be actually very useful. So I guess my question then is, have you thought about that, and is that sort of how you're approaching this, or where are you on that, in that line of thought?
Well, I'm actually very close to this line of thought. For me, for instance, many people in AI try to solve letting the machine understand very complex sentences. But I would already be very happy if I could just tell a robot something similar, something simple like bring me the newspaper, something with 4 words maybe. So if maybe the robot at first doesn't understand newspaper or some other word, I want to have a system which is able to ground those words incrementally based on what it experiences. So for instance, the caveman dog you mentioned, so that things like this becomes possible. I don't want the system to speak perfect English or something like that. For me, it would already be very impressive if it, like a child in early development, if it can acquire the meaning of individual words and associate them or relate them to something they experience or to something they have experienced around them. So in the sense, it's also close to this event processing paradigm. You just throw in events, and some events of them come from your auditory sensor and correspond to certain words. And you want the system to be able to associate those words in a multimodal way with other things which are ongoing. And this is really what I find most interesting. I don't think, I'm not very interested in in having a system speak or understand perfect English. I think that's a very long road, but I would already be happy if it could understand the meaning of a few words and relate this meaning to what it sees and to what it does, and so that the meaning or the grounding issue of words goes simply away by the relationships the system creates in itself with other things it has seen, with other things it has heard, with other things it observes to be happening. And so I'm actually very close to this philosophy that let's start with simple language. And
that's excellent. Yeah, that's sort of language in the service of intelligence rather than intelligence in service of language.
Exactly. Mm-hmm. And I'm personally, for instance, I don't like to introduce much complexity in this system. I want to see how far can you get by keeping things simple and see, for instance, even when this system does planning, for instance, I can show a quite interesting example.
Patrick, I have to interrupt you.
Oh, okay.
Let's move all this discussion to the afternoon because we are supposed to start at 1:30 for the workshop. Okay, now it's already too long, I guess, for everybody. Let's take a break and resume all this discussion at 1:30. How about that?
Sounds good.
Peter, what should we do for this channel? We just leave it here, or we need to shut it down and restart it. I have no idea, but anyway, let's resume at 1:30.
Right.